Hello, and welcome back to my YouTube channel. My name is Professor Gavala, and today I'm going to be talking to you about the common emitter NPN bipolar junction transistor. We're going to be reviewing the input impedance, the output impedance or resistance, and the AV voltage gain, the gain of the transistor. So to begin, we need to first label some variables or label some components, and note that this is the collector, this is the base, and this is the emitter. And the reason why it's called a common emitter is because the emitter is connected to ground. And also remember, in a BJT configuration, we have this resistance R pi located right here. And this is the small signal circuit to the right, where we can consider that we have an IO, output current, maybe flowing through this RO is an IOI, and then back out is a IO again. And in this situation, we also have an I input or an I in that flows and then also flows in here. So let's start by finding the input resistance Rin, and we note that Rn is valued for Vn is equals to Vn over In. And if we do a KVL right here, we note that this is minus Vn plus R pi times In is equals to 0. And essentially Vn is equals to R pi In. So our input resistance of this common emitter BJT is Vn over In, which is equals to R pi. So now let's find the output resistance. So R out is equals to VO over IO, given that V in is equals to 0. So here we want to essentially create and make this equal to 0 and do some circuit analysis. And the first analysis we're going to do is a KVL here again. And we could say that minus Vn plus V pi or VBE is equals to 0. We know that Vn is noted as 0 per our constraints right here. So as a result, V pi, which is equals to VBE, is equals to 0. The second thing is we can do a KCL in respect to this this output current. So we can say that IO is equals to IO1 plus GM VBE. Again, this current flowing through here is GM VBE. And as a result of that, we can consider IO1 to be equals to IO minus GM VBE. We know that VBE is equals to 0. So this term ends up just being IO1 is equals to IO. We can consider this to be our first equation and this to be our second equation. And then the last equation we can do is we can do a KVL in this loop. And again, we know that the voltage across this RC resistor is VO. So we could say then that minus VO plus the voltage through this resistor is RO times IO1, which is equals to 0. And then VO is equals to IO1 RO, which is just simply equals to IO RO. And as a result, R out is equals to VO over IO, which is then equals to RO. So this is our output resistance of the common emitter NPN BJT. So now let's find the gain. The gain AV. So we're going to write the AV gain here. And this is equals to VO over VN, or V out over VN. And again, we remove this constraint we had earlier of VN being 0. So VN is no longer 0. And we consider our equations again. So if we were to, let me erase so it's easier to see. If we were to consider that we do a KVL in this loop, right here, we would say that we have minus Vn plus VBE is equals to 0. As a result of that, VBE is equals to Vn. Again, remember VBE is equals to V pi as well. So this is our first equation. Equation 1. We can also go ahead and write a KCL in respect to this IO. And we could say IO is equals to IO1 plus GM VBE. And as a result of that, we can solve for IO1 and say that this is equals to IO minus GM VBE. But we know that VBE is equals to Vn. So we can say that IO1 is equals to IO minus GM Vn. Another equation we could write is IO in terms of VO. And we know that IO is going through this resistor. So this is IO. So if we write a node voltage between ground and this node here, we say that 0 minus VO over RC is equals to IO. So then IO is again just negative VO over RC. So this could be considered my second equation, and this is my third equation. And the last equation that's necessary for this analysis is this KVL right here. And we can go ahead and say minus VO plus, again, because this is a plus minus RO IO1 is equals to 0. Let's go ahead now and plug in our values for IO1. So this is minus VO plus RO times IO minus GM VN. And we could equate that to 0. And then we could say then that this is minus VO plus RO times, because of equation 3 right here, we could plug IO into here, and we could say that this is minus VO over RC minus GM VN. This is equals to 0. And now we have all of our terms in terms of VN and VO. So this is V out plus RO times minus VO over RC minus RO GM Vin is equals to 0. Let's go ahead and pull these two values to the right-hand side. So we get on our left-hand side minus Vin times, let's do Vin minus GMRO is equals to V out RO plus RO over RC. Again, I'm taking that from, sorry, this should be 1. So this is move to the right-hand side. This is 1, and then pull out a VO. I'm left with RO over RC, and it becomes positive because I move it to the right-hand side. And then to finish this off, so AV is equals to V out over V in. So this is going to be equals to minus GM RO over 1 plus RO over RC. Now imagine if we were to multiply this by RC over RC, we would get that AV is equals to minus GM RO times RC over RC plus RO. So this is your complete AV gain of the common emitter BJT. But then we need to consider some simplifications. And that simplification is when RO is much greater than RC, which is normally the case. This is around 10 to 100K ohms. And this can be, depending on your specifications, can be from anywhere from 10 to like 10K ohms. So depending on your specifications, RO is normally a lot bigger than RC. So we can consider the AV to be, imagine this is minus GM. In the eyes of RC, this is infinity times RC over RC plus infinity. Infinity plus RC just becomes infinity. And we cancel these out. So this is approximately minus GMRC is my AV gain. So I hope this makes sense. If you have any questions, please leave them down in the comment sections below, and I'll be sure to get back to you. And this is the AV gain of a common emitter. Please like, subscribe, and share my videos. Thank you. Have a wonderful day.